We have, of course, talked about substitutions, and we've talked about these as well, but let's look at it in a bit more detail where we're actually going to substitute in x. If the integral involves the square root of a squared plus x squared, I should try and create the trig identity underneath. So if you see a squared plus x squared, you would use a tan theta. So you create your a squared plus a squared tan squared. If you see a squared minus x squared, either a sine or a cos, you could use for that. And the other possibility, of course, would be x squared minus a squared. That's where I'd use a sec theta. And what it allows you to do then, of course, is your square root. Instead of having two terms under the square root, you can use your trig identity to make it one term under the square root and then find the square root of it. So, well, this is a standard one, but let's use it as an example to prove where that standard integral comes from. 1 on the square root of a squared plus x squared, so I'll use the substitution a tan theta. So dx becomes a sec squared theta to theta. So substituting in the dx is a sec squared theta to theta. A squared plus x squared becomes a squared plus a squared tan squared, which is a squared sec squared. Square root of a squared sec squared is a sec, and the a's will cancel, leave me with the integral of sec theta. And we've seen now that the integral of sec theta is the log of sec plus tan. I now need to substitute in for sec plus tan, so I'll draw myself a triangle. We said tan theta was x on a. The hypotenuse, not a coincidence, it'll always turn out to be what the square root was, because that was the whole point of the substitution we're doing. So we get the square root of a squared plus x squared. So sec is the square root of a squared plus x squared over a, and tan is x. So you notice the standard integral is actually x plus the square root of a squared plus x squared. There's no a on the bottom. Because all we now do is we say, well, to use our log laws, I can go minus log a, but a is just a constant, so it's still that plus a constant. And that's where the standard integral comes from. X on the square root of 1 minus x squared. So I'll let x equals sine theta. Dx will be cos theta to theta. Subbing in, I've got sine theta cos theta on the top. Square root of 1 minus sine squared, but 1 minus sine squared is, of course, cos squared. Square root of cos squared is cos, which will cancel with the cos on top, leaving me with sine. Integral of sine is minus cos. Draw up my triangle. We, in this one, have said sine theta is x over 1. The other side, again, turns out to be the square root. And we're reading off it for cosine theta, so it's minus the square root of 1 minus x squared. Now, of course it is, because if you have a look at it, it is in fact the derivative times the function to some power. We could have done it that way. So, x squared plus 3. So here's one where I'll use tan theta. In this case, it'll be root 3 tan theta. Dx root 3 sec squared. So subbing it in, the root x squared plus 3 will become root 3 sec theta. The dx becomes root 3 sec squared theta. I get 3 times our lovely integral sec cubed theta that we saw yesterday. Now, that we do by parts, you may remember. So sec theta and sec squared. U is sec theta. Du is sec theta tan theta. dv will be sec squared, so v is tan theta. And so I get 3 lots of uv minus v du. My integral now is sec theta tan squared. I change the tan squared to be sec squared minus 1. And I end up with, oh, there's sec cubed again. But I've got 3 times the integral of sec. Well, I know what that is. That's the log of sec plus tan. I now look at it like, oh, well, this is something I know to be true. Let's draw on the triangle so I can also substitute in. Now, notice what I've done. I've said 3 lots of the integral of sec cubed theta. I've gone right to the top and said that's the same as the square root of x squared plus 3. That way I don't muck around with how many am I moving and things like that. I know I've just got that integral. And I've converted each of the other ones as well. Moving to the other side, so 2 lots of the square root of x squared plus 3. Divide by 2. You might want to just get rid of the root 3, put it in the constant. It's up to you. I did because it looks neater. So there's my answer. Okay. So a handful of those to try. That's just in Patel.